Unit 9 is of huge importance to AP Calculus BC. This is the sequences and series chapter. It is what I like to say the granddaddy of them all as far as the units are concerned. This is the beefiest one as far as what separates AB from BC. It's going to start off with a concept called sequences, which are basically functions, and it's going to move on to turn those sequences into series, and then we're going to look at extended infinite series and see how we can use them to approximate more complicated functions. It's really cool stuff, and hopefully you share my enthusiasm of it. Real quick, another shout out to Mr. Corpy. You can read that. I don't need to read it out loud. All right, so a sequence is nothing but a function. The only difference between a sequence and the functions that we define in terms of x is normally our input is not x, it's n, the number n, and n is not any real number. N tends to be a positive integer. So instead of a continuous function, we tend to be talking about these discrete values, just a list of numbers in a particular order. So for example, the first term can be called a sub 1, and the second term can be called a sub 2, and the third term can be called a sub 3, where the subscript is the input, is the n value. So the nth term is going to be called a sub n. Why are we using a? Why not? That's like the f in f of x. It's just the name of the function. We could have one sequence called a sub n and another sequence called b sub n, and those are just different names for different sequences. All right, and we can express sequences in a couple of different, or several different ways. One, we could just create a list like this. This is just a very simple list of all the counting numbers. And we use dot dot dots to indicate that it continues if it's an infinite sequence, which they normally will be in this class, separated by commas. Okay, another way we could give it is as an explicit rule. For example, that's like your f of x equals 4x over 3 plus 2x. This is a sub n equals 4n over 3 plus 2n. Same idea, again, except x is not going to be, instead of using x as a continuous variable, we're going to use n as a discrete variable, and n again is going to go from 1 to infinity, but just the integers. Every once in a while we might see a sequence defined just as a rule set off in braces. So instead of having the a sub n equals, we would just have just the braces here and the rule. I don't tend to use that one too much, but it might show up from time to time. A fourth way we could do this is recursively, and instead of talking about recursive right now, we'll talk about it as it comes up. Recursive. All right, so if you're going to try to find the first 5 terms of a sequence, it's as simple as evaluating a sub 1, which is 4 times 1 divided by 3 plus 2 times 1, which is going to be 4/5. A sub 2, and we're just going to replace the n with a 2, so we're going to get 8 on the top, and 3 plus 4, or 7, on the bottom. And then a sub 3, it's just evaluating this expression for different n values. That's really all it is. So 4 times 3 is 12, and then 3 plus 6 is 9. If you feel like reducing it, go for it. I'm not going to worry about that. A sub 4 is 16 on the top, and 3 plus 8 on the bottom is 11. And you might notice a pattern here, an unsurprising pattern, but the numerator is going up by 4 each time, as you might expect, based on its definition. And the denominator is going up by 2 each time, again, as you might expect, based on its definition. So anyway, those are the first 5 terms. You could just write it as 4/5, comma, 8/7, comma, etc. You don't have to write the a sub 1 and the a sub 2 each time. Anyway, so that's the big idea behind sequences. It's just a list, an ordered list of numbers. Very often we're interested in what's happening to these sequences as the index n goes to infinity. So if we evaluate the limit as n approaches infinity of 4n over 3 plus 2n, yeah, we could use L'Hopital's rule, but we know better. The easier way to do this is just look at the coefficients, right? We have an exponent of 1 and 1. The degree is 1 on both the top and the bottom, so we look at the coefficients of 4 over 2. Basically, this is just asking the question, what is the horizontal asymptote of the function? Okay? So that is probably the number one question we're going to be asking about any particular sequence is what is its limit as n approaches infinity? And that answer is going to be able to determine the type of sequence it is. It might be a convergent sequence or it might be a divergent sequence. That is the big question of this entire unit, whether we're talking about sequences or series. The question of whether the sequence or series converges or diverges is of utmost importance. So we say the sequence converges if the limit as n approaches infinity is a real number. For example, 2, like we just got. If the limit does not exist, then we say the sequence diverges. Now, just a quick reminder of ways that limits may not exist. The limit may approach infinity, in which case we would say the sequence diverges to infinity. The limit may approach negative infinity, in which case we would say the sequence approaches negative infinity. The other way that we are going to see where we'll get a divergent sequence is due to oscillation. And we might see that with trig functions, but that's not the only time we'll see it. Remember that if your sequence is not approaching a single value, for example, if it might be bouncing back and forth between -1 and +1, then it is not a converging value. We say it diverges. Even though it's not going to infinity, it diverges by oscillation. So there are 3 different ways that we're going to see divergent behavior, and only one with convergent behavior, namely when the limit exists and it's a finite value. All right, so we'll see some examples of that, but before we jump into that, let's make sure we understand this function called the factorial function. We haven't really needed it too much in this course up until now. Those of you who know about combinatorics and permutations will recognize this, but n factorial is n exclamation mark, and it is defined recursively. In other words, to find the next factorial, we need to know the previous one. So, for example, just 0 factorial is defined to be 1. 1 factorial is going to be 1 times 0 factorial. Well, that's just 1 times 1, which is 1. 2 factorial is defined to be 2 times 1 factorial. The 1 factorial we just said was 1, so 2 times 1 is equal to 2. 3 factorial is defined to be 3 times 2 factorial. Well, we know that 2 factorial is 2, so 3 times 2 is equal to 6. 4 factorial is defined to be 4 times 3 factorial. So 4 times 6 is 24. 5 factorial is 5 times 4 factorial. 5 times 24 is 120, and so on. So this is a sequence of values, 1, 1, 2, 6, 24, 120, etc., that we're going to want to be very familiar with. And again, the reason we're calling this recursive is because to find, for example, 5 factorial, we need to know what 4 factorial is, and we're going to multiply it by the previous value. So that's this part right here. Now, if you expand this out, you're going to notice that 5 factorial is the same thing as 5 times 4 times 3 times 2 times 1. So that's another way you can think about it, and that's what this other part of the equation is saying. But it's often useful to think about this in recursive forms because of, well, basically because it's easy to reduce sometimes when you have this recursive definition in your head. All right, so I already mentioned that sentence, so now let's take a look at some examples, several examples. Well, maybe I'll do these in the next video.